Okay, calculus, we talked about dot product, which is a scalar created when you perform the operation between two vectors. Now you have the cross product. Normally, when you're in 2 dimensions, if two lines are perpendicular, they meet at a right angle, and there's not a third line that's also perpendicular to them. But it's kind of easy to see in 3 dimensions that that's not the case. For example, the x-axis and y-axis meet at a 90-degree angle, but the z-axis meets both of them at a 90-degree angle, which means sometimes it's nice to find something that is orthogonal to both of the given vectors, and this process can be done using the cross product. It is most often calculated in standard unit vector form, and it yields a vector. It also can be called the vector product. Now, the definition of cross product is if you have u and v are 2 3-dimensional vectors, the cross product u cross v is this combination of multiplies u2 v3 minus u3 v2i minus u1 v3 minus u3 v1j plus u1 v2 minus u2 v1k, which is actually similar to a determinant of a 3x3 matrix set up with ijk across the top, and then the vector u entries, the u components across the second row, and the v components across the third row. So if you've done matrix multiplication before, this would be pretty easy. So let u equal I minus 2j plus k and v equal 3i plus j minus 2k, find the following u cross v. So the way I will set this up always is matrix style, ijk. We let u go across the front, the coefficients, that's 1, -2, 1, 3, 1, -2, v coefficients across the bottom. Okay. So the way matrix multiplication works, it's I times -2 times -2, which is 4, 1 times 1, which is 1, 4 minus 1, minus j times, when you get rid of j's, a row and column, that leaves the outside, so that's 1 times -2, which is -2 minus 3. I'll write this down here, plus k times 1 plus 6, because it'll be 1 minus -6. So that should be 3i. This is -5, but there's a negative here, so plus 5j plus 7k. Which is another vector. This vector should be orthogonal to the other ones, which means if you do the dot product with them, you should be able to check that it works. 3 times 1 is 3, 5 times -2 is -10, 7 times 1 is 7, 3 minus 10 plus 7 is 0, which means orthogonal. 3 times 3 is 9, 5 times 1 is 5, 7 times -2 is -14, 9 plus 5 is 14, minus 14 is 0. So notice this thing is orthogonal to both of those. So we have done u cross v, so what does v cross u look like? It's the same thing, just flipped. So all this is really going to do is change the numbers on the insides here backwards. So that ends up being -3i minus 5j minus 7k. So what happened between these two? All the signs flip. So that means, unlike the dot product, the cross product doesn't have the commutative property because of the way matrix operations work. If you switch 2 rows, you get the negative of your answer previously. I'll let you guys check v cross v, but this is still orthogonal to both vectors. So that's something interesting that happens. So these are all the properties of the cross product. Again, it's not commutative, but if you change the order of cross product, it becomes the opposite sign, all terms. The distributive property, though does hold. U cross v plus w is u cross v plus u cross w. If you multiply the whole thing by a scalar, you multiply one or the other by the scalar. The cross product across the 0 vector is still 0. Anything cross itself is 0. And actually the dot product relative to a cross, this is a weird reassociation. U dot V cross W is equal to U cross V dot W. It's just an interesting thing that occurs, and I don't know that we'll ever use property 6 much, but it is something that happens. Okay, so geometric properties of the cross product. U and V be non-zero vectors in space, and theta the angle between them. U cross V is orthogonal to both U and V. The magnitude of U cross V equals the magnitude of U times the magnitude of V times sine theta, where theta is the angle between them. And if U cross V equals 0, then they are scalar multiples of each other, which means U and V are parallel already. And the magnitude of U cross V is the area of the parallelogram having U and V as adjacent sides. Okay, so find a unit vector that is orthogonal to both U equals I minus 4j plus k and V equals 2i plus 3j. So what we have to do is do the cross product to find a vector and then do what we have to do to make it orthogonal, or make it a unit vector, which means find the magnitude and divide all terms by that. So again, it doesn't matter which one we do first because both of them we find are going to be orthogonal. So this will be, I'm going to do 1, -4, 1, 2, 3, 0. So we've got I times 0 minus 3 plus j times, minus j. 0 minus 2 plus k times 3 minus, looks like -8. That is -3i plus 2j, looks like plus 11k. Okay, but that's not a unit vector, but it is the vector -3 to 11. To find the unit vector, I need the length of this thing. That'd be the square root of 9 plus 4 plus 121. Square root of 134. So I need to divide all of those by the square root of 134. So the unit vector is -3 over the square root of 134, 2 over the square root of 134, 11 over the square root of 34. And we'll do more in the next video.